let's introduce our first speaker for the day. So our first speaker is Vignesh Balasubramaniam from AMD. So he is a member of technical staff with over 8 years of experience in compilers, debuggers, and he's the guy in our team that debugs the debugger. So you can probably guess how much he knows just from that. He's here to give a talk on OMPD and OpenMP debugging interface. So yeah, without much more delay, Vignesh, please, the stage is yours. Thank you.
I'm Vignesh. Today I'd like to talk about this OMPD, OpenMP debugging interface. If some of you familiar with OpenMP framework, you probably heard of this at least because it's in the standards. Let's go. The agenda I have is like a small intro and states about when and where it started, all those things, and what is OMPD, a definition from the OpenMP API standard. Then quick intro to OpenMP if some of you are not aware of what is OpenMP and the framework is. Then why is OMPD is required and the need of it, and why is it in standards. And then I'm going to cover a few sections from the standards which belongs to OMPD because you probably require that if you're going to work on the OpenMP tools. Then architecture of like what is currently in LLVM. We have OMPD that supports GDB debugger, which is present in LLVM. I'm going to talk about architecture of those, and then what is libompd.so. It's basically OMPD and what it does. Then a plugin code, that's what we call an interface between libompd and then a debugger. Then the flow. I had this heading just to make sure, like when you run a small GDB with the OMPD enabled, how the flow goes and which part of the component that you touch upon and then to enable things. Okay. Then finally, testing directory, what we have in LLVM, just to give you a heads up, like where you want to add your test cases and all. It was introduced in OpenMP 5.0 around 2018. However, the discussion was started around 2013, a long back. Specifications includes both OMPT and OMPD. If you don't know what is OMPT is, stands for OpenMP Tools Interface, and OMPD is for Debugging Interface. The OMPT is used by Archer. The tool is already in LLVM, which basically detects the data races and OpenMP programs. More to say, like it's actually not detected data race. When you run the OpenMP program under the LLVM sanitizers, you get a lot of false positives because sanitizer does not understand the OpenMP runtime, and that's when this tool comes into the picture. It removes all the false positives for you and then give you only genuine failures. Then Total View Debugger has this OMPD support. Probably for a long time there is a blog about it, you can go ahead and read. And then OMPD is introduced in LLVM by AMD around 2021. There are around 7 or 8 set of patches that you can go through, very small set of patches and easily understandable. I mean, post this talk you'll be able to understand, I guess. Then it was originally designed and developed by Joachim and others in OpenMP Tools Interface. If you are from OpenMP community, you know there is a Git repo called OpenMP Tools Interface, specifically designed to put OpenMP specific tools there. So you can see there that the original code was there. It only supports C and C++ right now on Linux, what is in LLVM. Somehow it won't support Windows and other OSs. Only support host and does not support the GPU. However, if you are interested in GPU, you can go to that OpenMP Tools Interface Git repo. Joachim has some of the code that belongs to CUDA. All right, what is OMPD? OMPD is just an interface, what do you call, a set of APIs that allows you to inspect the OpenMP runtime. This architecture is designed in a way that OMPD only interacts with the debugger or third-party tools, doesn't need not to know about how the debugger interacts with the OpenMP program. The same way, debugger only interacts with OMPD and need not to be aware of the internals of the OpenMP implementations. So that allows the flexibility of this decoupling. That means you can run your program in a remote machine, and then you can debug it from some of the host machines that you sit. And then your libompd and debugger runs on the host machine, whereas the OpenMP program runs on the remote machine. Intro to OpenMP, like if you're very much aware, OpenMP, that's fine. If not, OpenMP, okay. If you have ever worried about getting your program run faster, you probably get in touch with this p-thread, get into the multi-threaded program, right? But what are the problem with the p-thread is you always have to synchronize the thread. You do a lot of work, and the headache is actually maintaining the code. But that's where the OpenMP comes as handy. It contains a set of compiler directives, library routines, and then environmental variable with which you can easily control the OpenMP, any program to run it as a parallel. Let us take this small program. You can see there is one construct here. This is called a class. If you want to understand the standards, that you can go read a lot of constructs are there. But this is a directive, and this is a directive, and this is a library routine, the API that you call from your program. Okay. So what happens is when you say parallel, and then code under this scope, right, runs parallelly and into the number of the threads that you meant here. Like you say, when you said 4 threads, and this code inside runs 4 times. That's what OpenMP, you just have to put a code and then say OpenMP parallel 4, and that will run for you for the 4 times. And then you can come up with the questions like how to synchronize. Synchronize will be taken care by the OpenMP in the background. Okay. For example, you can take imagine a program where you want to call a function with input, where input is from the array of 4 indexes. Okay. Now you can, instead of calling function a of 1, function a of 2, you can simply call it in a program with it. And then there are a lot of API like this which allow you to control which thread you want to execute on which part of the code. All those things are available in OpenMP. There is a for loop construct, there is a task construct, there are different kinds of construct that enables you to control your parallelism as much as you want, more control over given to you, okay? So if you see here, the program starts here. As soon as it sees this construct, the program starts a 4th thread, and that 4th thread goes and executes this region, and then when it becomes the master thread only execute the return statement. As soon as the code crosses the parallel region, it becomes 1 thread. So inside the 4th thread, I have made there is one constructor here asking to execute the function call only 1 times. This is like insane code. Don't worry about the code. Just try to understand the part of it. When you say single, it will call the functions only 1 time. 1 thread goes here, and there is one more parallel construct here which will initiate a 2 worker thread to run the printf function. So basically, your printf prints twice by this parallel construct, right? The code flow something looks like this. You understand how the thread is divided, where it goes. Looks here. So this is how the OpenMP works. There are like more than hundreds of constructs that you easily confuse when you really write an OpenMP frame program, and then if you try to debug. So what is the problem with this OMPD is? OMPD actually uses a thing called libomp underneath. When you compile a program, you can see there is a libomp library that gets added to your program, and then that's when it actually uses all these controls and all there. So what happens is the thread creation, the synchronization, everything happens at the libomp level, which GDB does not aware. That is because that comes from the library, right? So what happens when you put a small BT of look, this BT is from that earlier program. You have only 15 lines of program, and then you have 15 stack traces. Like, how do you try to manage it? That's kind of hard thing if you're really working on OpenMP program. And if it is more of like nested level parallelism, then you really have a headache of finding which thread you're actually debugging. That's going to give a more uncomfort of finding out where it is. Otherwise, you have to rewrite your program with some of the print statements to understand it. So instead of that, if OMPD is developed very well, then you can simply remove those stack traces here and then see where it is actually coming from. The first stack trace you can see is very simple, saying the thread that you're running actually come from this particular line. So that line, that parallel construct actually created a thread. So if you want to, so this program is saying like OMPD BT on continue, then you can continue your backtrace all the way to the main program. I'm going to show you a couple of more examples, which are like how you can utilize OMPD when you debug it, like, right? This is not for debugger. If you have other third-party tools, some of the scripts, automated tools, then you can use libompd as well. And then, yeah, so if you see the previous program, and then if I break this function, right, the function here, then when I run the parallel, OMPD parallel command, which will gives this many informations. So these kind of informations which you never get from the GDB, unless you know the OpenMP implementation, goes to the OpenMP, try to go the nitty-gritty of that. That is hard for someone who are actually debugging the OpenMP program, right? And then this is one more command, ICVS, that stands for internal control variables. In OpenMP standard, you can say it says like this control variables controls the OpenMP runtime. So all these variables are important. Each of these belongs to one of the scope. So you can see there is something called address, parallel, thread, and task. So OMP is divided into so many threads, like address space is one instance of OpenMP program, parallel space is kind of a parallel region, and then your thread means it belongs to one thread region, task means you have a task constructs, and then that particular variable belongs to the task construct, the task region. So these are the variables that currently have some values which you can use it to identify what is happening inside the OpenMP program. Okay, now these are from OpenMP API specification itself. I've just copied it. I just want to touch about major headings of OMPD in the OpenMP specification. In case if you're going to develop something on OMPD, you probably know where to look and what is to look. And okay, the first two things is activating a third-party tool. For example, if you have a debugger or any third-party tool and you want to use libompd, then you have to find the libompd and load it, right? Because libompd is something different from the libomp. You don't compile your program with the libompd. You compile your program with the libomp runtime, and then when you want to debug it, libompd is what is required, but you never know where it is. And that's where this comes, this OMPD DLL locations, which says when you try to use this variable and then print it, you can see like this variable as a string where the library is loaded. So if some of the times, like if OpenMP is not initiated, then they have given this another variable called OMPD DL locations valid. What it says is like when you don't find the variable or null in OMPD DL locations, you put a breakpoint here, and whenever I get that variable get initialized, right, when your OMP get initialized, OpenMP get initialized, and that will initialize this variable, and once it is initialized, it will come through. Your code flow come through this. So when you break it, you come here and then you see there is a libompd here. This will be populated. This variable will be populated when you break it here. I'll show you in the screenshot of the coming slides, but just remember there are a couple of things like this. And then data types, which is very common for any standard or any module that you define your own data types instead of confusing it with 32 or 64-bit like that. Then the one important thing is like this third-party tool callback interface. If you see this decoupling technique allows you OMPD to interact only with the GDB, not with OpenMP runtime. And then if OMPD cannot interact with OpenMP, then there is no way it gets to inspect the information from the OpenMP runtime, right? And it's supposed to use some other way of interacting with. That's where this callback interface comes into the picture. And the callback interface are the functions that basically interacts with OpenMP program on behalf of OMPD. So when you initialize the OMPD, you initialize with this callback interface. So if OMPD wants to do some of the things like allocate a memory, symbol address lookup, read memory from the OpenMP runtime, all those things goes through the callback interface, which again goes to the GDB, and GDB will do that for you, right? So if you see, for just a simple understanding, you can see take a allocate memory. libompd gets loaded in a process space of GDB. And if you do your own allocation, then that will be a difference, right? You must want to use the allocator of what GDB does. And that's some of the callback interface that you have declared in the standard. And then this is the important thing. These are all the functions, just the APIs. As you can see, it will get some input and give you output. That's all this API is. These are actually a core of libompd. You can see all these things are again divided into respective scopes, address, thread, parallel, and then, for example, let's take this thing. OMPD get current parallel handle. That means it will give you the handle of current parallel region. When you call this function with the input that is required, it will give you the current parallel handle. And the handle is nothing but some housekeeping variable that happens in the libomp in the backend, right? It's not some just a structure that has the information about the parallel region. And then there is this one is important thing. If you see, these are for only like around 4 different things: parallel, task, thread, and device. And then what it says is entry and exit point of those. So the thing is like, for example, in the libompd runs in a GDB workspace, and then your libomp runs something. If you want to interact the libomp to the libompd, what you say is these are even things. So whenever the thread is created, these functions get called. This is not implemented in OpenMP. You're supposed to go and put this function call in the libomp then and where required. And the standard also defines when this should be called, where this should be called. For example, when the thread is created, you go and put that OpenMP BP thread begin. That function is get called. Either you can have a global variable, load the data there, which OMPD can use later part. Otherwise, you can simply call it as a OMPD location valid as a breakpoint, and then you do your job there. So these are the event thing from the libOMP runtime. And yeah, the architecture. So as you see, this GDB and OpenMP programs, right? These are already there, existing. You consider any program, GDB debug it for you. Interaction between the done is already. If you are more interested, you can start with the ptrace on that. These two are existing ones, and these two are what we added near to the LLVM. Look, this is libompd.so. We'll see next what is libompd.so. This is basically implementation of those APIs I've shown you. How this APIs, implementation APIs. And this plugin code is interface. For example, when you called OMPD BT, so where does it land? The interface code. And then what it will do, it uses the libompd API and then gives the information. In order to give you the information, it goes to libompd API. The API again callbacks to this, to the OpenMP program and comes here. Okay, you can see the flow, right? So all these are interlinked. What in the libompd.so is basically implementation of all, definition of all those APIs. All the APIs takes input as an argument. I mean, the arguments are the part of like, input will be one of the argument and output will be one of the argument. You don't return as some value or some pointer. So you pass a pointer as argument and then it gets filled and comes back to you. Right? And then error code or success code is written so that you can see whether your API is succeeded or not. It basically inspects the libOMP runtime through, it goes to the interface again. If you see, it goes to the interface, goes to the GDB, and GDB get the data that required for the libOMPD and give back to the interface, and then it will come back to the libOMPD. And it mentions like it should be provided by the OpenMP implementer. The main reason behind is like, you know what data, where it is available in the OpenMP runtime. If somebody implements OpenMP runtime and then you go, if another guy implemented libOMPD, is not possible because those APIs depend upon some of the data from the libOpenMP, right? And this says that. And as you said, the decoupling thing, and GDB does not need to understand about the implementation of details of the OpenMP runtime. However, again, same goes with the libOMPD also. If needed, the third-party tools can be notified by certain events by runtime. That is means like what are the events we saw, right? If your tool required to understand whenever a device is initialized, you want to do something, then you implement that event and then put a breakpoint here on a GDB, or you say inside the tool you can call one more function that will be a call to your third-party tool. Something like that you can develop yourself and then use it. And these events are implemented in the runtime, not in the libOMPD. This definition of those events are in the part of the libOMP, not in the libOMPD because for obvious reasons. Plugin. Okay, here the plugin has, if you see OMPD space BT and OMPD parallel, and those are not the command that GDB knows about. GDB doesn't have that command, right? So you have to initialize that command, introduce that command to GDB, and all those stays here in the plugin. And then you define that command and what that command is supposed to print, everything here the interface code. Again, this plugin acts as interface between the GDB and then your libOMPD when the libOMPD wants to access the libOMP. Right? And very important thing, the callback functions of OMPD was defined here. For example, libOMPD as of now can only interact with the interface, right? So when they say I want to call back this allocate memory, then it comes to the interface. Interface says whether you have to call malloc or some GDB underscore alloc, and that's from there it goes back again. For example, read the symbol addresses of some variable. If OMPD wants to read some symbol addresses, then what it will say is I want to read symbol addresses. So the callback function control goes to the interface. Interface read it for you through GDB APIs, right? The important thing is that libOMPD can be used on other debugger. For example, LLDB can use the same libOMPD, but the interface should be changed. That's what the importance is. Those two blue color boxes, right? If you change this, you have to change this as well. Saying if you change this, you have to change this as well because both are dependent. These both are dependent and the two are dependent. Right, the flow. Okay, what I'm trying to do is I'll run one GDB command and then I'll do what we basically do with this LLVM right now. You have a small OpenMP program there, what you have seen earlier, and then I'll put a break there at line number 8 and run this OMPD parallel, what I've showed you. What I'm trying to show you is like how OMPD works internally when I run those commands, and how this API and then interface are interacting and gives you the data. Okay. This is where you have a GDB command. We start with the GDB and then saying there is something init.py. The Python is the interface that we have used in the LLVM. What it says is like enable the GDB, enable the GDB with OMPD kind of. So what this init.py will go and enable this OMPD, BT, parallel, all those commands, and then tell the GDB that you have this new command or something like that. That's when you run this OMPD init next, GDB understand there is a command called OMPD init. Okay, that's what the first things does. Just initialize all those new commands. And then when you run the OMPD init, basically these four things will happen. Load the libompd through the DL open, and then call the OMPD initialize functions with the callback that OMPD requires, and then initialize the address space with OMPD process initialize. The address space is, you can consider this as one kind of checksum, one for the one OpenMP program instance. Like if you have two different programs, you will be having two different address spaces, right? And then it breaks at the BP thread begin. So why we are doing at BP thread begin is whenever the OpenMP thread is created, we want to capture it and keep it somewhere. When somebody access, now give me the number of thread that has been created, I'll give information. So there are, this is what the event is, right? This is event is. This event is gets called whenever the thread begin is happen. Okay, now you can see it here. This is a GDB. So this is what underneath happens when you try to load the libompd to real open. You basically start it. If you run this command start, you have these DL locations, right? It's just at the main. You can see DL location is not available. That means OpenMP is not yet initialized. And then I put a breakpoint on this DL location valid. Then I continue. Then it stops there. It need not be a big function. It can be just some small instructions where you can easy for you to break it there. You can see that variable is loaded with this many things. You can, if you see the library libompd.spo in already existing LD library path, use it. Otherwise, you pick it from the wherever the libomp is there, right? That's where this is basically. So one of for you to understand how we use this the OpenMP DL locations that we have seen there in the standard things, right? How we use this. If you try it in thing, it might not be possible if you try it by yourself, because I've enabled a libomp with the debugger. I mean -g enabled. That's why you're able to print this variable. Sometimes you only get the addresses. You have to typecast into it, because a lot of the libomp that you know deployment stage, you don't have the debuggers available. I mean debug information available in the library. Okay. Now what happened? Then I put the break at line number 8, and then I continue it. You can see it stops at every time the thread begins is called. Okay. So internally, how it works is like in the interface code says like whenever GDB breaks at this particular OMPD BP thread begin, come to me. Then the interface stores all those thread in some housekeeping variable in order to show you later that yeah, these are the OpenMP threads like that. Got it? So you can see that this gets break there, and then finally it comes to the 8, the parallel region of the function. So next, this is the OMPD parallel command where you see all those information is get printed. Okay, so you can see it, right? It basically says how many parallel regions. I mean, not how many parallel regions. It says that you are a nested parallel region. There is one more parallel region on top of it. And how many number of thread that it has, basically it says 4, and then 2, what is the current thread, and then thread state of each thread, and the nesting level is there, okay? So now what I'm going to show you is how do we take this information from the libompd API. Okay, let's take this team size. If you want to have a team size is number of threads inside the parallel region. If you want to have a team size value, what you're supposed to do is you have to call this particular API, OMPD get ICV from scope. When you say ICV, you have to give the handle and then scope. So what we are supposed to be, the team size variable, if you see the standard, it belongs to the parallel region. So we have to give a parallel handle and then parallel scope. And then this ID means is ID that belongs to, that identifies this is the team size variable. And then your output comes into the ICV value. But this is not going to be easy when you have, you don't have a parallel handle, right? When I say OMPD parallel, I don't have parallel handle. How do I get a parallel handle? I call this function. There's something called OMPD get current parallel handle. That will give me the parallel handle. But again, in order to get the parallel handle, I need a thread handle. So I call these functions with a thread ID. So when I call these functions with a thread ID, which needs like address space, the thread ID, how do I know thread ID? Because GDB knows what thread I'm currently running in. Okay, so when you say the thread ID, pass that ID to this particular API, and that will give you a thread handle for you. You pass that thread handle to this function, and then you get the parallel handle here, you pass it here, and then it will give you the ICV variable that you can easily print it here. ICV is team size. The same goes to the nesting level, and then everything else, same goes to. Only thing is it need not to be the same as this, but there is a different hierarchy of the function call happens inside. That it get to decided by the interface. That means whoever write those commands, what you wanted to be get out of it. And then if you see this old, this function, there's a thread kind and size, all those things. This is because not all the libOMP implementers are supposed to use the pthread. They might use different one. So when you implement those, you are supposed to understand what arguments are passed to this. So some implementation details you should be knowing it. Okay, so now line number 8, right? Now I wanted to have a thread handle. So inside for the thread handle, I need a thread ID. So this particular variable has a thread ID that is currently executing. So when I say p KMP GT ID, it will press 0. So what I have to do is I have to use this particular variable on this index. I'll get a thread handle. So once you get a thread handle, you can look for the team that this thread handle belongs to, and then you get the parallel handle here. So once you get the parallel handle, you basically say what level I'm in, nesting level, or number of process, that means number of threads I have. That's what happens here. So you cannot simply print this out if you run any libOMP with a debugger, because this is not, this is having a debug information enabled. That's why you're able to do it. If not, what you have to basically do is you have to understand what kind of variable it is, what type of variable is it, 64-bit or 32-bit integer, and then get the address it from the GDB. These are the global variables. So GDB basically understand, like gives you the address. If you print, for example, if you take any GDB and then OpenMP program and print KMP GTID, it will give you the address. But it will not show you how many number of bytes this particular data type has. So in order to know the data type, the OMPD guys know. So they typecast the data type to that and then get the value out of it. That's what happens here, right? So once you get the team size, you can, the way that you print it is however you want handy. And then for the nesting level, you use this variable T level. Similarly, when you know the implementation of OpenMP, you get to know what kind of variable holds what value, and then you put that value in when you run the OMPD commands.
So this is all possible only if you compile with debugging.
This is all possible if you compile with the libOMP debug information. This is possible. But you, as when you are debugging OpenMP program, you don't want to know what variable holds what value. Instead, I simply say OMPD parallel and get all the informations, right? So I have a lot of information in the OMPD parallel, but which thread I'm executing, what is the state of those thread and all. But now I have to go find the thread number first. Multiple commands you have to execute, and only if you know the internals of implementations. Like if you know the implementation of libOMP, then you can go and print this variable as details and print it. But if some other OpenMP guy who only writes OpenMP program and doesn't want to know the implementations, right? He can simply call the construct and get the parallel region. He doesn't want to which variable in the OpenMP holds this value and all. That's again a complication for him. So this is the two-way. If you don't have debugger, then you can do this way. If you have a good tool, you can develop the tool like this and then make use of it. Okay, so this is for the parallel region. Parallel region, there is one more API. If you see the first one, it's only for the first level of parallel region. There is a nested level, right? For the nested level, you can call this get enclosing parallel handle. So what this API gives and what happens, you can read it in the standards. It's very easier. So when you call this, it will give you the parent parallel region that called this particular thread, right? So it will give you basically, if you see between previous, we have this there is a one thread handle, and then there is this T is a parallel handle. If you come here, you can see T, I call the parent parallel handle, and then I put the T level and proc. Basically, it says your nesting level is 1, and then there is a 4th thread, right? Okay, so how, now we talk about like when you interface has this OMPD parallel, and what kind of API that you call, and what kind of information that will return, and how do you print it. Now you probably want to know how this API is implemented, right? This API is implemented is same as this. When you call this enclosing parallel handle, it probably, you said some parallel handle, API is supposed to give the enclosing parallel handle. So you will give up to this T value to the API, and then API will simply give you T parent pointer operator and then T. That's what it does. But it's not straightforward as it is. Because in terms of when API is implemented, API, for example, take this case for the thread handle. API know that when somebody is asking me a thread handle, I have to take a variable called KMP threads, right? And then they'll also give a thread ID. I have to go to that index and get the thread handle and give it to you. Basically, this is what this API has to do, right? But it is not simple. It's what it gets initially is the address of it. GDB only give you the address of the global variable, because if you see libOMP doesn't have any debug information. It just says thread. So now the API is supposed to cast it to some type, because it has its own headers file, and then it will cast it to the data type and find a size of it, and then read that memory from the OpenMP runtime, basically using the callback interface. Now you understand, right? You go back to the callback interface, give the addresses, and then say read this many bytes from this many address, and then it will give you this. So now you increment it, go to the second index or whatever the index you want. If you want the data of 5, then you can increment that size from the address you got to 5, you go to that pointer. Now you get that. So once you get this structure, right, whatever this KMP threads of index structure, then you should, as a OpenMP implementer, you would be knowing that there is a TH which has the handle of thread. So how do you get that? It may be a structure pointer, or it may be a structure itself. If there is a structures, you know which byte to which byte the size of that handle is and how to read it. Again, you call back use the callback interface, tell the GDB to read this address, this many bytes, you get the thread handle, right? Otherwise, if it is a pointer, you have to go to the address of that, and then again take the address. If it is a pointer, it will be holding address, right? You take that address, cast it to a type, find a size, and then again call back that. This is what happens here. This is how the OMPD API is implemented. But these are implemented in a simpler way, something called target value.c or .h file if you see in the LLVM. It has its own way of doing these things. That will be, you don't have to touch any of those, but yeah, this is how it happens underneath. Okay, I think I covered everything, bit of interface, how the libOMPD API is defined, and let us move on to this testing part. We have 3 different testing framework for this thing. It's always, everything is a simple one. So one is similar to what LLVM uses, a lit framework. It has this you have this command, and then you have the check strings. So how do you run this command is basically you call a GDB, you compile it first, and then you call a GDB with that command file. GDB has option of -x. When you give -x, it will read from the file. For each line of the file is a command, and then it executes it here, and then it prints in a big file. So that file will take it and look it for whether your expected strings or the numbers that you're expecting is there or not. If it's there, it's there. This is the easy one. And then this was developed by Joachim itself. There is something called OMPD tool test. It's not a big thing. There is a function defined in OMPD, one of these testing.h files. This is the OMPD tool test. You can see that file. It basically collects the data of thread parallel task and things. How did it collect? Through the OMPT. If you read the standard, OMPT is again a tool interface which gets the data from the runtime and store it. So they load this data. First they collect the data, load the data, and break it at particular point, the OMPD break null. So now the interface that we have designed knows whenever the program breaks at OMPD tool break, control goes to the interface, and the interface actually compares this data using the OMPD APIs that it has. Say whether it's right or not. So it is very simple. You write any program, and then you put this particular call wherever you want. any of this parallel region, any of the thread region you want, and you simply test it for yourself, and then finally it will say whether OMPD mismatch is happening or not. If it is a mismatch, then there is a failure. Some of the cases is failing. And then this is test API. This is one more command that we have introduced in OMPD, basically just to test whether it is returning the code or proper as per the standard. So what it does is anywhere, similar to the OMPD tool test, anywhere you can put this particular break at any point and then call this test API with some of the API. What I'm saying is get current pair handle, you can call thread handle, whatever it is. So what it do is first it check with the proper arguments and then see whether it is returning a proper value or not. And then say whether it passes or not. If not, it will go for another mock input and then test you whether it is giving a proper return code. In case if you're changing the libompd API, you probably have to test whether you're returning a proper code or not. Yeah, I think pretty much covered. That's it. If I can take questions, I can take, otherwise. Yes.
So does that mean you didn't have to make any changes to the actual source code of GDB?
No, you don't have to. You don't have to.
So that means I can use it with any debugger like LLDB
No, that's the problem. Is the interface code is specifically designed for debugger, GDB.
So we can re-implement interface itself to work with other debuggers.
Yes. So when you change the blue box, you're probably supposed to change this debugger as well. That's what I'm trying to say. One second. When I say OMPD BT, right? So GDB says the Python like GDB import Python GDB model. Import GDB and then GDB add command OMPD BT. But LLDB might having something. You have to do LLDB add command OMPD BT, right? And that kind of places you have to change it. Similarly, the callback interface is also here. GDB might say print some variable, you get the address. But in LLDB, it might be different, right? So those changes here. So if you change this, this will also get changed. So this will be developed by these guys, whereas this will be developed by these guys.
Okay. Fine.
Yeah. So in one of the slides, when you were invoking GDB, you had a init.py. So you mean to say that the interface is developed in Python for GDB?
Yes.
Okay.
The interface is developed in Python. Basically, you have a GDB Python model.
So how much, like, what is the kind of complexity you have for the Python interface for this? Like in terms of like lines of code, maybe like how?
Okay, the lines of code might be around 1K lines of code, which is spread over 3-4 files.
Okay.
But if you see in a Python, it's not straightforward as because you have 4 or 5 commands. The 4 or 5 commands have separate init functions and then super functions, all those things.
Okay. Okay. And the library itself is stateless. The library does not hold any state. Whatever the interface that you are writing, that has to hold the state and make sure it is passing the right input to OpenMPD at each point,
right?
So that it gets the right output to show the user.
Right. Because the interface handles things, right? That's supposed to say like what I'm going to do with this data is known by the interface only.
Yeah.
Then interface holds the data. If I need a number of threads, if a command says give me number of threads, then I have to do the thread data. Then I hold it. Yes.
Yeah.
When you handle when the instance comes from the GPU, then you the variables might be different in cases, for example, right?
Right.
So those things you have to handle in the API. So what it says is like if it is built for okay, you can go on this OpenMP tools interface, whatever the Joachim has developed. There is a CUDA code that actually contains a GPU's thing. But I don't think it is fully developed. You have to check through it. But you can offline. You can connect with me. I'll help you with that.
I have a question.
No, we don't have Windows support.
Can you use it on the Photon programs as well?
No, Photon.
It's only for the C
okay. The
programs.
problem with the bindings, right? When you say the mangling name that you get of this OMPD get parallel API, that's supposed to fit with the Photon when you run it, but easily extendable for even Windows and Photon. But somebody has to put work on. We have removed some of the things because we don't have time or resources. But if you want, we can do that. It's not a big issue, but you can try it out. Yeah.
I think I didn't understand this. Is it supported for the open offloading as well?
Offloading as of now, no. As of what does in LLVM is not supported, but what this Joachim code in OpenMP tool interface, right, have some of this CUDA support. Maybe you can check with it, but we removed it when we upstream it because we don't have the infra to check the CUDA as well as resource to check for the CUDA. But if you want to go and try those repo, you probably have some of the code that might be hanging there. You can just port it to this thing. It might be working. Yeah.
Okay, thanks.
So basically, sir, what will be the constraints when I move to Windows? Like it is in a ISO file, right? So
Yes, that's a constraint. So if you want to, it has to be compiled for the DLL file. If your DLL file, okay, if you see, I mentioned GDB interface code, open the library through DLOpen. So DLOpen, how do you open the DLOpen? And then you can call the function DLSimb, find the OMPD get current parallel handle, and then you call it. But when you run it with compile for the Windows, this OMPD get current panel DLSimb won't be working, right? So you have to interface also, you have to change that it works for the DLL file.
okay.
Okay, and then you probably don't have a GDB in Windows. Then you have to support that interface because you're changing the blue box. You have to suppose change the blue box again.
Yeah, hi. So I just wanted to ask, like, is there any mechanism in OpenMP to handle data races? For example, considering the printf case. So depending on the implementation, if it is a non-atomic printf, so in that case, like, is there any mechanism we could use, like, for data cases?
You're asking whether OpenMP handles the data race itself?
Yes.
Yes, it does.
Okay.
OpenMP, okay. When you say parallel and then you do whatever you want, inside it, OpenMP is supposed to take care that you should not execute two things. For example, when we say this dump threads 2, right, here we have so many classes. Like what are the variables used inside, whether can be shared or private to thread. We can all pass information to that when you write the hash pragma parallel construct. When you do that, you inform that OpenMP runtime that I wanted this particular variable to be a...
There is a thread sanitizer and also those, that kind of...
Thread sanitizer actually finds data race in between the threads, right? That's what initial discussion I told you, right? That's called Archer tool. What happens is when you run a thread sanitizer on an OpenMP program, thread sanitizer is a different way of handling it's whether this is atomic read or not. And then it might say like it is already reading by twice, and then it say that there is a data race. But what happens is the atomicity is taken care by internally by the OpenMP, which is not aware to what thread sanitizer. And that's where the tool like Arches comes to the picture, which basically tells the thread sanitizer that, yeah, I'm taking care of this atomicity between this and this, so don't worry about it. So basically when you say thread begin will pass to the thread sanitizer, and again, if you as long as you use one kind libOMP from LLVM, you can use a libompd.so from the LLVM. But if you're using libgomp from GCC, then you have to use their OMPD. As you said, because this particular variable, right, we're talking about KMP threads. That's where the thread handle is.
Exactly.
And that thread handle variables belongs to libomp.so. When libgomp comes, that might be a different variable, and you have to change your API definition to pick that variable instead of this variable.
I had a follow-up question. I mean, it's really good to see such a good tool exist. I didn't know. But what are the production use cases of this? How do people build some additional tools on top of this for their
for this OMPD, no. For OMPD, no.
There's only for developers, if I understand.
Only for developments,
Right.
basically for the developments.
There's no use case as such apart from...
For this tool, if you see this OMPD parallel command alone, this is only for the debuggers to use it.
Exactly.
But if you consider that you are developing a tool for a parallel libOMP something, then you can use this API in order to get those informations, and you have this lot of opportunities to different kinds of tools with that API, right? For example, like you are writing a profiling, then you need some of this to understand, or OMPD tools to understand how many threads are running, how many number of times that it will be running BP thread begin and BP thread end. Okay, those level of opportunities is different. So what we have shared is basically how we use this libOMPD in terms of debuggers. And it's more designed for debugger only.
I was just thinking, like, is there any use case in production? Okay, without this tool, nothing is going to work or something like that.
You can, if you can think through, maybe you can, if somebody is implementing a program, if you want to performance of lifetime, then there is a hook, OMPD thread begin, thread end, right? Parallel begin, parallel end. Then you can see how many parallel regions are created and what is each time is taken up. Okay, something like that you can think of and use it.
Okay.
That again, their architecture board gives you this API. You can do whatever you want as per your imaginations.
Okay, that makes sense.
That makes sense, yeah.
How do you avoid false positives and sanitizers when you are using libopenmpd? Because right now you illustrated something with GDB.
No, sanitizers use not libOMP. It's use
Okay.
OMPT. That's a different tool
Okay,
altogether.
okay. Oh, okay, okay, okay.
You
Yeah,
can
yeah,
go inside the LLVM, OMP, OpenMP tools called Archer.
Okay.
I think 3 or 4 files.
Okay.
Which basically uses this OMPT APIs. What I've showed you, the standard is OMPD. Similarly, there is
OMPD,
called
yeah, yeah.
OMPT APIs.
Okay, okay.
That uses to understand when the thread is begin and when the thread is ended.
Okay, okay,
And then it informs the sanitizer. When the sanitizer gives the information, it removes the false positive out of it. It's very simple tool. You can probably go and spend half a day, you can read it and understand.
Okay.